Hi guys, welcome to our third lecture on phase equilibrium. So last time we talked about condensed phase equilibrium of 2 and 3 component systems, and this time we'll now talk about liquid vapor equilibrium of binary liquid systems, which has many applications in separation techniques like distillation. Okay, so again, before we begin, let's consider the variables that we'll be investigating. So let's just calculate the variance of our binary liquid system. Okay, so the general equation for variance is, recall, F is equal to 2. Okay, so this 2 over here corresponds to temperature and pressure, plus C, the number of components, minus P, the number of phases. Okay, so of course, since we're dealing with a two-component system, C is equal to 2. Okay, so right now F is equal to 2 plus 2 minus P. Okay, so for the most part, however, we'll be keeping either temperature or pressure constant. Okay, so ultimately this value over here is going to be equal to 1. Okay, so overall F is going to be equal to 1 plus 2, so 3 minus P. Okay, so 3 minus P, this is when we hold either temperature or pressure constant. Okay, so this is our overall variance. Okay, so overall we could either plot temperature or pressure against our composition. Okay, so the types of systems that we'll be investigating will include the following. Okay, so first we'll be considering a completely miscible binary liquid system. Okay, so we could consider first an ideal solution, the simplest case, and then we could extend our treatment to non-ideal solutions. So we'll just look at the ways that our non-ideal solution can deviate from our ideal solution. And then next we'll look at the case when we have a partially miscible liquid system, and then we'll finally look at the case in which our system is completely immiscible. Okay, so first let's look at our first case. Okay, completely miscible system. Okay, so overall let's consider mixing two components A and B. Okay, so if you consider the pure component A, okay, so we know that's going to be in equilibrium with its vapor. Okay, so it has a corresponding vapor pressure of pure component A. Okay, so that is signified by P sub A naught. And we could also consider component B. Okay, so component B is also going to have its own characteristic vapor pressure, which we can call P sub B naught. Okay, so what happens if we mix these two things together? Okay, so we know that they are completely miscible in the liquid state. Okay, so if you mix them together, we form a homogeneous mixture of A and B. Okay, so this is going to be based on how much A and how much B we're going to be mixing together. Okay, however, what is going to be the composition of our vapor? Okay, in other words, what is going to be the vapor pressure of the solution? Okay, is it going to be just the addition of these two pure vapor pressures? Okay, so let's investigate that in a bit. Okay, so let's just recall Dalton's law of partial pressures. So the total gas pressure of a mixture is just going to be the sum of the two partial pressures of the components. Okay, so in this case it's going to be the partial pressure of A plus the partial pressure of B. Okay, so if we look at this over here, okay, so we have to wonder, is this going to be equal to the pure vapor pressures? But we have to consider the fact that A and B actually interact, so there might be some changes in the corresponding vapor pressures of our components in solution versus when it is in its pure state. Okay, so let's just recall what determines the vapor pressure of a liquid. Okay, so if we have a liquid over here, then we have some of those molecules escaping into the gas phase. So the amount that escapes into the vapor phase at a certain temperature, this is going to be characteristic for the liquid, and it tells us something about the intermolecular forces of attraction of that substance. Okay, so overall, at a given temperature, the liquid will just have a certain amount of kinetic energy, and that kinetic energy can be used to overcome some of the intermolecular forces of attraction. Okay, so in general, if we have a greater intermolecular force of attraction, that means that our liquid needs more energy in order to escape into the vapor phase. Okay, so this implies that at higher intermolecular force of attraction, we have a lower vapor pressure. Okay, So when we look now at a mixture, okay, so we're going to be having different types of molecules interacting with one another in the liquid, okay, so again the same principle holds, however. So you still need to have a certain amount of kinetic energy in order to escape into the vapor phase, okay, so the overall escaping tendency will depend on the different intermolecular force of attraction present in the mixture, okay, so this will include the intermolecular forces of attraction between the like particles, okay, so AA and BB interactions, and also for the unlike interactions, okay, so that means interactions between A and B, okay, so it will also depend on how much of each component there is in the mixture, okay, so overall this will tell us how many like interactions we'll have and how many unlike interactions we might have as well. Okay, so we could characterize each of our solutions based on the different types of intermolecular forces of attraction that we have between the like and the unlike particles, okay? So the first case I will be considering is the ideal solution, okay? So in this particular case, the interactions between the like, that is AA and BB interactions, are approximately equal to AB interactions or unlike interactions, okay? So examples of solutions that can be approximated as ideal solutions include ethanol and methanol and benzene and toluene, okay? So just note that they have very similar types of intermolecular forces of attraction, okay? This implies that if you have a mixture of these two things together, okay, the intermolecular forces of attraction of unlike are going to be very, very similar to the like interactions, okay? So if ever a benzene molecule encounters a toluene molecule, it's going to be treating it very similarly to if it encountered another benzene molecule, okay? So let's get a visual picture of all this happening over here, okay? So here we have our solution, okay? So if you have an ideal solution, this implies that all of these interactions over here, okay, so like interactions here of pure A, okay, so we have interactions here of A, B here for the mixture, okay, then we have pure B over here. That means that all of these interactions are equally favorable, okay? So interactions of the mixture are not favored over interactions of a pure system, for one, okay? If we consider the vapor pressure then of our solution, okay, it's going to be dependent primarily then on the relative amounts of each of the components, okay? So for example, so if you have a mixture that is richer in component A, okay, the vapor pressure of the mixture will be more characteristic of the original vapor pressure of A. So if we have more A in the liquid, it's also expected that we'll have more A in the vapor phase, okay? So same thing goes if we have more B, okay? So if we have more B in our liquid phase, okay, the vapor pressure of the entire solution will be more characteristic in the vapor pressure of pure component B. Okay, so we can express this mathematically using Raoult's law, okay? So Raoult's law tells us the partial vapor pressure of each component in an ideal mixture, okay? So that is just given as the mole fraction of component I in the mixture times the pure vapor pressure of component I, okay? So that will overall give us the vapor pressure of component I in the mixture. Okay, so combining Dalton's and Raoult's law can also give us an expression for the overall vapor pressure of our solution, okay? So recall from Dalton's law that we could get the vapor pressure of a solution by just adding the corresponding vapor pressure of component A in the mixture plus vapor pressure of component B in the mixture. Okay, so Raoult's law just gives us these expressions here, okay? So overall we know that the vapor pressure of component A in the mixture is going to be equal to the mole fraction of A times its pure vapor pressure, okay? So we also know a similar expression for B, okay? So this is going to be equal to the mole fraction of B times its pure vapor pressure, okay? So overall, we could get an expression for the vapor pressure of the solution as the mole fraction of A, okay? So mole fraction tells us the composition of the mixture, right? And we could just multiply this by the corresponding pure vapor pressures of our components, okay? So overall, this is our expression for determining the vapor pressure of a solution, okay, for an ideal solution. Okay, so it's just going to be dependent on composition and the corresponding pure vapor pressures of our components, okay? So also as a reminder, okay, so just keep in mind that since we're dealing with a two-component system, this means that the mole fractions of A and B, okay, so in general, of course, this is just going to be equal to 1, okay? So you just need to know the composition of one of the components and you could easily calculate for the composition of the other one. Alright, okay, so another important thing to keep in mind here is that we could also calculate the corresponding composition of the vapor phase, okay? So note here that when we're calculating for the vapor pressure of the solution, okay, so this composition here, okay, so mole fraction A, mole fraction B, this corresponds to the composition of the liquid phase, okay? The vapor phase, on the other hand, is going to have its own composition. So overall, while chi A and chi B gives us the mole fractions of our components in the liquid phase, okay, so YA and YB on the other hand give us the mole fractions of A and B in the vapor phase, okay? So actually we could also make use of the principles that we know from Dalton's law in order to investigate what the mole fractions of A and B are going to be in the vapor phase, okay? So recall again that if we have a mixture of gases and we're assuming that we have ideal gas behavior, we know that the P solution is just going to be equal to PA plus PB. Okay, so we could also write this in another way, right? We could also write this in terms of mole fractions, okay? So mole fraction in the gaseous phase, however, okay? So the mole fractions we'll be using in this case, okay, this is going to be equal to our YA, okay? So this is just to differentiate it from the mole fractions in the liquid phase, okay? So YA times P solution plus YB times P solution, okay? So overall, we know that PA, the vapor pressure of A in the solution, is going to be equal to YA times P solution, okay? In other words, YA is equal to PA over P solution. Okay, so we could expand this expression based on Raoult's law. Okay, so we know that PA, this is going to be dependent on the mole fraction in the liquid phase. Okay, so this is mole fraction of A times the pure vapor pressure of component A. And we could also expand our P solution to that expanded expression that we had over there. Okay, so we could also have mole fraction A times pure vapor pressure of A plus mole fraction of B times pure vapor pressure of B. Okay, so overall, this over here, this tells us the mole fraction of a certain component A in our vapor phase. Okay, so it's going to be dependent actually on the composition of the liquid phase as well. Alright, okay, so always keep in mind, guys, that we're using the notation of chi A, chi B for the composition in the liquid phase, and we used YAYB for the composition in the vapor phase. Okay, so please do not get too confused about this here. Okay, so with all these in mind, we could actually plot a vapor pressure composition diagram. Okay, so for our particular example, we'll be using B as the more volatile component. Okay, so since we know that B is a more volatile component, this implies that its vapor pressure, its pure vapor pressure, is going to be higher compared to that of A. So we can plot that over here. Okay, so overall the vapor pressure of B is going to be around this value over here, and we expect that the vapor pressure of pure component A is going to be lower. Okay, so to complete our phase diagram, okay, so we'll be connecting these 2 points over here with sort of a bubble like this, okay? So labeling all this, okay, so at high pressures, we expect that our mixture is going to be in the liquid phase, okay, so we have a single phase over here, a homogeneous liquid mixture, so therefore our P is equal to 1, variance is equal to 2, okay, so on the bottom over here, okay, at low pressures, okay, so we expect that we have a vapor phase over here, okay, so homogeneous vapor phase, P is equal to 1, F is equal to 2, so in between here, however, this is where we have liquid and vapor in equilibrium with one another. Okay, so overall our number of phases is equal to 2, okay, so vapor and liquid, so our variance is equal to 1. Okay, so how could we interpret this diagram over here, and what do these lines mean exactly? Okay, so let's just redraw this in a bit. So the top line over here, okay, so this line here, this represents the liquid line. Okay, so if we're looking at the bottom line over here, this represents the vapor line. Okay, so the way that we could interpret this is that if we have a system that has a vapor and liquid in equilibrium with one another, okay, we could use a liquid line and the vapor line to determine their corresponding compositions, okay? So say that we have a system with a vapor pressure of the solution as P, so the place where our vapor pressure of our solution hits the liquid line, this tells us the composition of the liquid. Okay, so overall composition of the liquid, this is characterized by mole fraction A, mole fraction B, right? Okay, so where it hits the vapor line, this tells us the composition of the vapor. Okay, so this is characterized by YA, YB. Okay, so assuming that we have a perfectly ideal solution, this over here, the vapor pressure of our solution as well as the vapor compositions can be calculated using Raoult's law and Dalton's law. Okay, so we could also investigate what happens if we have a system of a fixed overall composition, and you can see what happens if we decrease the pressure, for example. Okay, so let's start with a composition of 15% B and 85% A. Okay, so say that we start with this particular pressure over here. Okay, so if we are at this particular pressure, we can say that the pressure is super high, that we actually don't have any vapor present. Okay, so we only have a liquid phase. Okay, so we could easily say that the composition of the liquid phase is equal to our overall composition. Okay, so 15% B, 85% A. Okay, so let's investigate what happens if we decrease the pressure. Okay, so overall we expect that if we decrease the pressure, we could start to see some vapor appearing. Okay, so let's decrease the pressure all the way to this point over here. Okay, so if we decrease the pressure all the way to the liquid line, this is actually also known as the bubble point. Okay, so note here that we just hit this area now. Okay, so we're in this area where we could see vapor plus liquid present. Okay, so once we just hit this line here, this tells us that we see the first trace of vapor. Okay, so the reason why it's called a bubble point is because this first trace of vapor just appears as a tiny bubble. Okay, so the composition of this tiny bubble over here, okay, so this can be determined using a tie line. Okay, so if we draw a tie line all the way to the vapor line, okay, this tells us that the composition of this bubble here is going to be around 50% B, 50% A. Okay, so you can see here actually that the component that goes into the vapor phase more easily is the component that is more volatile. Okay, so B is the more volatile component, therefore the vapor is always going to be richer in the more volatile component, okay, which is B in this case. Okay, so if we continue to decrease the pressure, so say now that we're going to be in between, okay, so we can see here that we have a lot more vapor present. Okay, so we can determine the corresponding compositions of these phases by drawing again a tie line. Okay, so let's draw out a tie line here. Okay, so if we draw a vertical line going down to the liquid and the vapor phases, okay, so we can see here that the liquid phase is going to be 10% B, 90% A, okay, so the liquid becomes much richer in the less volatile component, whereas the vapor becomes richer in the more volatile component. Okay, so note however that the vapor at this point is not as rich in component B as it was in the bubble point. So the vapor in the bubble point represents the composition of the vapor in which it is richest in the more volatile component. Okay, so as we continue to go down here, okay, so the composition of the more volatile component becomes less and less. Okay, so next we could investigate what happens once we hit the vapor line over here. Okay, so once we hit the vapor line, okay, so this is actually also known as the so-called dew point. Okay, so similar to the bubble point, the dew point represents when we have the last trace of liquid. So this tiny thing over here represents a dewdrop. Okay, note that since we pretty much boiled off our entire mixture, okay, the composition of the vapor is expected to be the composition of our overall system. Okay, so 15% B, 85% A. Okay, So the composition of the dew, however, can be determined using a tie line again. Okay, so we could draw a tie line from this point towards the liquid line. And overall, if we draw a vertical line over here, we could see that we have around 5% B, 95% A. Okay? Okay, so if we further decrease the pressure to below the vapor line, okay, so pretty much you have a vapor that is 15% B, 85% A, and you're just decreasing the pressure, okay? So overall, we could use vapor pressure composition diagrams to investigate what happens if we have changes in pressure on the equilibrium and composition of our completely immiscible binary liquid system, okay? Okay, so let's apply Raoult's law, Dalton's law, and vapor phase composition phase diagrams in order to solve this problem here. Okay, so we're at constant temperature and we have an ethanol-methanol ideal solution. Okay, so we're also given that the liquid solution contains 60% mole ethanol. Okay, so we want to calculate a bunch of things over here. Okay, so before we begin, let's try to sketch out really quickly a phase diagram. Okay, so we could also get a picture of what exactly we're solving for. Okay. Okay, so let's sketch out a phase diagram over here. Okay, so we have our plot here. Okay, so let's say that this is, I don't know, 100% methanol. Okay, so we have methanol going in this direction here, and we have ethanol here. Okay, so our temperature is at a constant 60 degrees Celsius, and we have our pressure on our y-axis. Okay, so let's also plot out the corresponding pure vapor pressures of our components. Okay, so if we have pure ethanol over here, the pure vapor pressure of ethanol is going to be 352.7 millimeters mercury. Okay, so let's just note that the pressure here is in terms of millimeters mercury. Okay, and then we also have the higher vapor pressure of methanol. Okay, so it's a more volatile component. So this is at 625 millimeters mercury. Okay, so we could just complete our phase diagram by drawing our curves. Okay, so we have our liquid line over here and we have our vapor line over here. Okay, so just label the phases. We have liquid, we have vapor plus liquid, and we have vapor on the bottom here. Okay, so our liquid solution contains 60% mole ethanol. Okay, so since we have our phase diagram on our sketch here in terms of methanol, so this implies that we have 40% methanol. Okay, okay, so we have 40% methanol in our liquid. Okay, so let's draw up a line all the way to the liquid line. Okay, so this is the composition of our liquid over here, and to figure out the corresponding vapor that is in equilibrium with our liquid, okay, we could draw out a tie line towards the vapor line. Okay, so this over here, when we draw out a vertical line towards the composition axis, this will tell us the composition of our vapor in equilibrium with the mixture. Okay, so this is question B. Okay, so to figure this out, this is item B. Okay, and then note, okay, that this tie line here, this is drawn at a corresponding pressure. Okay, so this pressure over here, this corresponds to the vapor pressure of the mixture. Okay, so this is for question A. Okay, so how about for C and D? Okay, so C, it asks for the composition of the last drop of the liquid before vaporization becomes complete. Okay, so it's pretty much asking for the composition of the liquid at the dew point. Okay, so this implies that just before vaporization becomes complete, this means that the composition of the vapor is going to be equal to the composition of the original liquid solution. Okay, so this means that the vapor, its composition is going to be equivalent to 40% methanol and 60% ethanol. Okay, so that means we have a composition along the vapor line. Okay, so this is the vapor line. Okay, so overall, this is going to be the composition of the vapor at the dew point. Okay, it's going to be 40% methanol, 60% ethanol. Okay, the same composition of the original liquid mixture. Okay, so if you want to figure out the composition of the last drop of liquid before vaporization becomes complete, okay, graphically this is determined by plotting a tie line towards the liquid line. Okay, so overall, if we draw a line downwards, this represents the composition of the last drop of liquid before vaporization becomes complete. Okay, so this composition over here, this is going to be for item C. Okay, so next we want to figure out the pressure at which the mixture will completely vaporize at 60 degrees. Okay, so this corresponds to a pressure here. Okay, so it's at this pressure at which we have complete vaporization. Okay, so the dew point. Okay, so this is going to be the pressure for item D. Alright, so hopefully using this diagram can help us connect which points we're actually solving for, right? Okay, so we can make a connection between the things that we'll be solving for using Raoult's law and Dalton's law with a corresponding phase diagram over here. Okay, so we just drew this phase diagram to give us a sort of visual picture as to what we're solving for, but all of these items over here can be solved for without a phase diagram. So we could just use Raoult's law and Dalton's law to answer each of these items over here. Okay, so first let's start with A, the vapor pressure of the mixture. Okay, so let's move on to a fresh slide over here. So overall, we know from Dalton's law, okay, so P solution, this is going to be equal to the vapor pressure of ethanol plus the vapor pressure of methanol in the solution. Okay, so expanding this using Raoult's law, okay, so we have P solution, this is just going to be equal to the mole fraction of ethanol times the pure vapor pressure plus the mole fraction of methanol times its pure vapor pressure. Okay, so we're just given again just the mole percent of ethanol, but we could easily calculate for the mole fraction of methanol, okay, based on the principle that if we add the mole fractions together, they're all going to be equal to 1. Okay, so overall the P solution, the vapor pressure of the mixture, this is going to be equal to, okay, so 0.60, okay, so that is the mole fraction of ethanol, times its corresponding vapor pressure, pure vapor pressure, so 352.7 millimeters mercury, plus, okay, so 1 minus 0.60, okay, mole fraction of methanol, times its corresponding pure vapor pressure, 625 millimeters mercury. Okay, so solving for this, okay, we just have 461.6 millimeters mercury. Okay, so this is the vapor pressure of our mixture. Okay, so how about the composition of the vapor in equilibrium with the mixture? Okay, so what we're solving for here is Y ethanol or Y methanol. Okay, so we could just specify the composition of one. Okay, so specifying the composition of one component in one phase automatically specifies the other one. Okay, so we know that we could define the composition of ethanol in the vapor phase as its corresponding vapor pressure in the solution over the overall vapor pressure of the solution. Okay, so this is just equal to, okay, so this is 0.6, okay, times 352.7 millimeters mercury. Okay, so this is the mole fraction of ethanol times its pure vapor pressure over the vapor pressure of the solution, which we just solved for over here. So this is 461.6 millimeters mercury. Okay, so solving for this gives us a value of 0.458, okay, mole fraction of ethanol. Okay, so we want to put this, if we want to put this in percentage, we could easily do that. So 45.8, okay, percent mole ethanol. Okay, so this is the composition of the vapor phase. Okay, so again, note that it is different from the composition of the liquid. Okay, so overall we have A and B down, so now let's solve for C and D. Okay, so let's move on to a fresh slide again. Okay, so note what we mentioned earlier about the nature of the composition of the last drop of liquid before vaporization becomes complete. Okay, we said here that the composition of, say, ethanol, okay, in the vapor phase is going to be equivalent now to the original liquid composition. Okay, so you pretty much just boiled off this entire solution. Okay, so if you boil off the entire solution, okay, if you have 60% in your original liquid, you're going to have 60% in your vapor. Okay, so overall the composition of ethanol in the vapor phase at this point, so let's call this prime here to differentiate it from A and B. Okay, this is going to be equal to mole fraction of ethanol in the original. Okay, so overall this is 60%. Okay, so this is going to be 0.6. Okay, so we can kind of work backwards from what we did over here in B, right? Okay, so how do we express the composition of ethanol in the vapor phase? Okay, we said that this is the pressure of ethanol, okay, so let's call this prime, over the vapor pressure of the solution. Okay, so expanding this over here, this is going to be equal to the composition of the liquid in equilibrium with this composition. So this is going to be equal to x chi prime. Okay, so mole fraction prime, this is the composition of the last drop of liquid before vaporization becomes complete. So we just indicate it with a prime to differentiate it with this value over here, times the corresponding pure vapor pressure of ethanol over, okay, so the vapor pressure of the solution, that is, okay, so mole fraction of ethanol times pure vapor pressure plus 1 minus mole fraction of ethanol prime. Okay, so this over here, this represents the mole fraction of methanol prime, okay, times the pure vapor pressure of methanol. Okay, so overall we know what this is over here, we know what this is, and this is. So we have one variable that we need to solve for, which is chi prime ethanol. Okay, so composition of ethanol in the last drop of liquid before vaporization becomes complete. Okay, so filling in all these, we have 0.60 is equal to, okay, so chi prime ethanol times its corresponding pure vapor pressure, 352.7 millimeters mercury, over, okay, chi prime ethanol times 352.7 millimeters mercury plus, okay, 1 minus chi prime ethanol times the pure vapor pressure of methanol, which is 625 millimeters mercury. Okay, so solving for the composition of ethanol in the last drop of liquid, this becomes 0.727. Okay, so note that the last drop became richer in the less volatile component. Okay, so how about for our last item over here, the pressure at which the mixture will completely vaporize? Actually, this question over here is pretty much just asking for this value over here. Mole fraction of ethanol in the last drop of liquid times its corresponding pure vapor pressure plus the mole fraction of methanol in the last drop of liquid times its corresponding vapor pressure. Okay, so we're pretty much solving for a pre-prime solution. Okay, so this is equal to 427 millimeters mercury. Okay. Okay, so overall, there we have it. We were able to solve for all of these items here without actually using a phase diagram. But just keep in mind that it is possible to solve for this if we do have a phase diagram. So it's just nice that we're able to draw a connection between the things that we're solving for and for how it's represented on a phase diagram. Okay, so overall we just investigated the effect of pressure on our completely miscible binary liquid system. Okay, so now we could look at the effect of temperature. Okay, so this time we could plot a temperature composition diagram. Okay, so note this is going to be a little bit more useful to us, especially for distillation applications. Okay, so temperature is much more easily controllable compared to our overall pressure of our system. Okay, so when we plot this, we're still going to treat B as our more volatile component. So if B is the more volatile component, this implies that its boiling point is going to be lower. Okay, so we can plot the boiling point of B over here, and we could also have the pure boiling point of component A. Okay, so this is very similar to our previous diagram. We could also have corresponding lines that are going to join these 2 points. Okay, so we have these 2 lines over here, but note that the way that we label our corresponding regions here are going to be a little bit different. Note that if we're going to be above our corresponding boiling points, we're going to have our vapor phase, and if we're going to be below, we expect to have our liquid phase. Okay, but in between over here, we're still going to have our liquid and vapor in equilibrium with one another. Okay, so again, note that for binary liquid systems, okay, the liquid and vapor could exist in equilibrium with one another in a range of temperatures. So this is in contrast with pure systems in which at constant pressure, okay, the vapor and the liquid can only exist in equilibrium with one another at a single temperature point. Okay, this, however, we see that we have a certain range of temperatures at which a vapor and liquid could exist in equilibrium with one another. Okay, so note again, let's just contrast this with our vapor pressure composition diagram. Okay, so note that the more volatile component will have a corresponding higher vapor pressure, and also note the different labeling of our regions over here. Okay, so you have a liquid on top for our vapor pressure composition diagram, and on the temperature composition diagram, we have the vapor on top. Okay, so just note these important differences, all right? Okay, so also note that we could interpret the temperature composition diagram in a very similar fashion to that of the vapor pressure composition diagram. So the same way that the top curve here represents a liquid line, okay, in the temperature composition diagram, the bottom curve over here represents the liquid line. Okay, so if you draw tie lines towards this line over here, okay, vertical lines going downwards could tell us the composition of the corresponding liquid phase. Okay, so in this diagram over here, you have the vapor line on the bottom. On our temperature composition diagram, our vapor line is going to be on top over here. Okay, so the major use of a temperature composition diagram in contrast to the vapor pressure composition diagram is that we typically use these types of diagrams for distillation applications. Okay, so we could use this for determining the corresponding compositions of our distillate and our residue for a simple distillation process. Okay, so just recall that distillation occurs when we want to purify a mixture. Okay, so say that we have a liquid mixture over here. So we just heat our impure liquid over here. So what tends to happen is that the more volatile component vaporizes out of the mixture more than the less volatile component. Okay, so this vapor is collected as it goes through a condenser. Okay, so this condenser pretty much just condenses the vapor that is produced from this heating process over here. Okay, and then overall we could collect the distilled liquid. Okay, so this distilled liquid is called the distillate, and anything that remains in our round bottom flask is just called the residue. Okay, so again, this is just a very simple distillation setup. Okay, so we could analyze what happens if we have a liquid and we increase its temperature. Okay, so let's use this diagram here in order to investigate a sample distillation process. Okay, so let's say that we start with 100 grams of a mixture that is 30% by mole B and 70% by mole A. So if we're at this temperature over here, our mixture is just a liquid, okay? But if we start to increase the temperature, say to when we hit the liquid line over here, okay, this is pretty much the bubble point, okay? So actually the liquid line is sometimes called the bubble point line as well, okay? So once we hit this bubble point, okay, as the name suggests, this is the point when we have the very first trace of vapor. Okay, so actually this vapor is pretty much just a single bubble, okay, but we could determine the corresponding composition of this bubble by drawing a corresponding tie line to the vapor line. Okay, so at this temperature 1, the bubble point temperature, okay, the vapor is expected to be 75% B and 25% A. Okay, so typically the bubble point composition is used as a basis to determine the expected composition of the distillate, but keep in mind that it's more of an ideal maximum. Okay, more realistically, we conduct distillations between these temperatures over here. So if we increase the temperature to temperature 2, okay, we can see here that if we draw vertical lines from the tie lines here, okay, we have a vapor that is 60% B and 40% A. So if we collect that vapor through the condenser as the distillate, okay, our distillate is going to be 60% B, 40% A, okay? So even though it's not as rich as it was in the bubble point, we still have some degree of separation, okay? So note that the original mixture was 30% B, but now we have 60% B in the distillate. Okay, so we could also determine the composition of the residue. Okay, so we could draw a tie line going down from the liquid line. Okay, so this tells us that the residue here is going to be 60% B and 80% A. Okay, so overall you have some degree of separation that occurs. So overall your distillate becomes richer in the more volatile component, whereas your residue becomes richer in the less volatile component. Okay, so of course this only tells us the corresponding compositions of our residue and our distillate, but it doesn't really tell us how much of each of the distillate and residue we actually have, okay? We could calculate that using the lever rule. Okay, so again, recall again that using the lever rule will allow us to calculate the mole fraction in the vapor and the mole fraction in the liquid, okay? So the mole fraction of the solution in the liquid phase, this is going to be given by, okay, so the liquid phase is going to be over here, the vapor phase is going to be over here. So that means if we're calculating the mole fraction in the liquid phase, we need to use the opposite distance, okay? So this is going to be equal to d2 all over the total distance, so d1 plus d2. Okay, so D2, this is going to be equal to 60 minus 30. Okay, so we could use the x-axis over here in terms of mole percent B to determine the distances. So this is just going to be equal to 30, whereas D1, this is going to be equal to 30 minus 20, so this is equal to 10. Okay, so the total distance over here, this is going to be 60 minus 20, or it's 40. Okay, so calculating this, the mole fraction in the liquid phase, okay, so this is 30 over 40, so this is equal to 0.75. Okay, so the mole fraction in the vapor phase, okay, so this is going to be, okay, so the vapor phase is over here, so we get the opposite distance, so that is d1 over d1 plus d2. Okay, so that is going to be equal to 10 over 40, or 0.25. Okay, so overall we could rename this as the residue, okay, in the context of distillation, and we could also rename this as the distillate. Okay, so if we're dealing with a 100-gram solution, okay, this implies that we have 75 grams of our original solution that remains as a residue, and this also implies that we have 25 grams that are collected as the distillate. Okay, so overall here, okay, so again we have 75 grams of our residue, okay, and then we have 25 grams as our distillate. Okay, so that 25 grams, that is 65% by mole B and 40% by mole A. All right, okay, so that is how we could use the temperature composition phase diagram in order to determine amounts and compositions of our residue and distillate during the distillation process. Okay, so overall we could also see what happens if we increase the temperature further. Okay, so if we increase the temperature all the way to this line over here, okay, we pretty much reach the dew point. Okay, so we don't really want to do a distillation at this dew point temperature over here, because this is pretty much the point where you just boil off the entire solution. Okay, so if you look at the composition of the vapor, it's going to be the composition of the original solution. Okay, so while your dew is going to be a little bit much richer in the less volatile component, okay, you're just left with a tiny bit. Okay, so overall the range of distillation temperatures that are most practical are between the bubble point and the dew point. Okay, but again, we typically use the composition of the vapor at the bubble point as a basis to determine the maximum possible separation that we could do for a distillation process, okay? But note again that we could actually run a distillation multiple times in order to achieve greater amounts of separation, okay? So note that if we conduct a distillation and we end up with a distillate that is 75% B and 25% A, okay, you could redo the distillation, okay, so you could make this as your residue, okay, and then you could run a distillation again, okay, so you could increase the temperature up until its new bubble point. Okay, so the new bubble point is going to be over here. This is the point where we see the first trace of vapor for the new liquid to be distilled. Okay, and then we could determine the composition of the new distillate. Okay, so we could draw another tie line. Okay, so with another round of distillation, the maximum purification that we could achieve is 90% B and 10% A. So you could run this distillation process over and over again until you end up with a distillate that is nearly pure B. Okay? So note, however, that this is going to be several steps of a simple distillation process. Okay, so meaning that you have to do it over and over again manually. Okay, luckily there is actually a technique that kind of adapts this, okay, and turns it into a single step process, and that is your fractional distillation. Okay, so the additional of your sort of fractionating column allows you to theoretically run multiple distillation processes in a single step. Okay, so within this column over here, you have a temperature gradient that is achieved, and as you go up, you have a series of condensations and vaporizations that occur until you pretty much run an equivalent of multiple simple distillation steps in one go. Okay, so ultimately when you collect your final distillate, it'll probably be very, very rich in the pure component. Okay, that is assuming if you have an ideal solution. Okay. So this is the major application of your temperature composition diagram. Okay, so next up, let's investigate what happens if we have non-ideal solutions. Okay, so we've been dealing with this diagram over here when we have an ideal solution. So ideal solutions, they pretty much follow Raoult's law. But more realistically, we rarely see this type of ideal solution, and we typically see cases in which we have positive and negative deviations. Okay, so this is due to the fact that the intermolecular forces of attraction between our components are not going to be similar. Okay, so if you have a positive deviation, you tend to see a maximum vapor pressure point over here, and you see these weird shapes over here. And if you have a negative deviation, you tend to see a minimum vapor pressure in our mixture. Okay, so let's investigate when we have a positive versus a negative deviation. Okay, so if you have a positive deviation, this implies that the intermolecular forces of attraction between the like particles are greater than the intermolecular force of attraction between the unlike. Okay, so for a positive deviation, the interactions between the pure components are more favorable than the interactions between the mixture. Okay, so this implies something about what happens when we have a mixture then. Okay, so if you have a mixture, the intermolecular force of attraction aren't that favorable, right? They're not as strong. So therefore, the mixture becomes more volatile. Okay, so this implies that the mixture is going to have a higher vapor pressure, and it also implies that our mixture is going to be more readily boiled. Okay, so if we consider the temperature composition diagram, we expect to see a mixture that boils at a lower temperature. Okay, so if we investigate the corresponding diagrams, okay, so the vapor pressure composition diagram is going to exhibit a maximum vapor pressure over here. Okay, and then for a temperature composition diagram, we see a minimum boiling point. Okay, so this point over here, okay, this point is called your azeotrope. Okay, so you're probably familiar with this term from your distillation experience. Okay, so the azeotrope, this is a mixture that boils with constant composition. Okay, so it's kind of analogous to the eutectic point in our condensed phase equilibrium phase diagrams. Okay. Okay, so we'll discuss the significance of an azeotropic composition in a bit. Okay, so an example of a non-ideal solution that exhibits a positive deviation is probably very familiar to you guys. So this is ethanol and water. Okay, so you know that ethanol and water mixtures, they typically exhibit an azeotrope at 95% ethanol. Okay, so the importance of an azeotrope in practical applications is that it represents the maximum composition in which we could have an effective separation of our mixture through distillation. Okay, so if you have a mixture that is, say, 30% ethanol and you want to purify that through distillation, you could only purify your mixture all the way up until 95% ethanol. Okay, so this is even if you use fractional distillation. Okay, so you could see here that if we have like our 30% ethanol, okay, and then we do a distillation, okay, so the distillate is going to have a corresponding maximum composition of this over here. Okay, so we're approaching a richer ethanol composition, and then if you do this again and again, okay, ultimately we end up at the azeotropic composition. Okay, so if you try to distill an azeotropic mixture, okay, what's going to happen here is that you have a liquid that is 95% ethanol, and then we'll find that the composition of the vapor is actually going to be the same. So if you collect a distillate at this point, the distillate is going to have the same composition. So there is no effective separation that can occur beyond the azeotropic composition. Okay, so even if you start over here at, say, 98% ethanol, okay, and you try to distill, it's ultimately still going to end up at the azeotropic composition. So that's why whenever we have ethanol as our reagent, we typically see it as 95% ethanol, okay? So absolute ethanol, which is 99% ethanol, are probably purified through different means aside from distillation, okay? So it's probably purified as 99% ethanol through membrane separation technologies or through dehydrating agents, okay? So that's why 95% ethanol is typically very cheap compared to your 99% ethanol, okay? So we could also see another type of deviation. So this is when you have a negative deviation. So this is when the intermolecular forces of attraction between the like particles is actually less than the intermolecular force of attraction between the unlike particles. Okay, so that means it's actually more favorable to have the mixture compared to the pure components. Okay, so overall, since you have stronger intermolecular forces of attraction in the mixture, this implies that the mixture is going to be less volatile. So this implies that the mixture is going to have a lower vapor pressure compared to the pure components, and it also implies that it's going to be less readily boiled. So that means that the mixture is going to boil at a higher temperature. Okay, so let's look at the corresponding phase diagrams of a non-ideal solution that has a negative deviation. Okay, so again, it's going to exhibit a minimum vapor pressure. Okay, and it's also going to exhibit a maximum boiling point. Okay, so again, we also have the corresponding azeotropic composition. So these are just mixtures that boil with constant composition. So an example of a system that exhibits a negative deviation is your nitric acid and water system. Okay, so we expect to see an azeotrope at 32% water and 68% nitric acid. Okay, so overall, these are cases in which we have completely miscible binary liquids. Okay, so we just discussed cases in which we could have an ideal solution versus non-ideal solutions. Okay, so now let's look at a case in which we have a partially miscible binary liquid system. Okay, so let's consider components A and B. Okay, so what happens if we mix them together and they're partially miscible? When we mix them together, we expect to have a solution of B and A, or an A-rich layer, and a solution in A and B, or a B-rich layer. Okay, so for our discussion on partially miscible binary liquids, we'll be focused primarily on the effect of temperature on the corresponding mutual solubility of A and B. Okay, so since we'll be investigating the effect of temperature on the mutual solubilities of A and B, the phase diagram that we'll be constructing is just going to be temperature versus composition. Okay, so here we have it over here. We'll be treating pressure as constant. Okay, so actually the phase diagram that we'll be constructing over here is going to be very, very similar to our ternary system in which we had a partially miscible liquid pair. Okay, so in this particular case, we'll be doing the same thing. Okay, so if we are in this region of our plot over here, we have a lot of component A and small amounts of component B. Okay, so in this region over here, we could treat A as our solvent and B as our solute. Okay, so that means we're going to have a corresponding solubility limit of B dissolved in A. Okay, so we have our solubility of B in A represented by this point over here. So that means if we are below the solubility of B and A, this implies that we have a single phase present, okay? So if we go beyond the solubility of B and A, however, we expect to see two layers, okay? So if we increase the amount of B while decreasing the amount of A, ultimately, once you reach this region over here, B starts to act as a solvent and A starts to act as the solute. Okay, so in this region over here, we could also indicate the corresponding solubility limit of A in B. Okay, so here we have the corresponding solubility of A and B. So that means if we are below the solubility of A and B, this implies that we have a single phase, and if we are beyond that solubility limit, we expect to see two layers. Okay, so we could investigate the effect of temperature on these corresponding solubilities. So overall, as we increase the temperature, we expect that the corresponding solubilities of A and B and A are going to increase. Okay, so that means we could dissolve more A and B and A. Okay, so we expect to see this type of curve over here. Okay, so overall, we can label the corresponding phases. Okay, so beyond the corresponding curve over here, we expect to see a single phase, so therefore the variance is equal to 2. Okay, so the single phase over here that we expect to see is a homogeneous liquid mixture of A and B. Okay, so inside the curve here, however, this is when we see two layers. Okay, so we see a B-rich layer and an A-rich layer. Okay, so very similar to our treatment for our ternary phase diagram. Okay, we could also use so-called tie lines to determine the corresponding composition of those B-rich and A-rich layers. Okay, so this time, however, the corresponding tie lines are going to be parallel to one another. Okay, so at different temperatures, we expect to see different tie lines. Okay, and all those tie lines are going to converge at a single point over here. Okay, so this point here, this is called your critical temperature. Okay, so this is kind of analogous to our plate point. Okay, so the critical temperature represents the point at which the compositions of the A-rich and the B-rich layers become the same, and the interface between the layers starts to disappear. Okay, so overall, on the left side of our critical temperature over here, this represents the compositions of our A-rich layers. Okay, so on this side over here, you have your A-rich layer composition, and on the right side over here, you have the corresponding B-rich layer compositions. Okay, so we can use the tie lines to help us determine the corresponding compositions of the layers if we have a system that is within this curve over here. Okay, so let's consider a system in which we have 40% B and 60% A at a corresponding temperature over here. If we follow the tie lines, okay, so we want to determine the composition of the A-rich layer. The A-rich layer is going to be around 15% B and 85% A. Okay, so if we want to determine the composition of the B-rich layer, that is going to be around 80% B and 20% A. Alright, so an interesting thing actually happens here is that if we have another system that is, say, 70% B and 30% A, okay, so it's actually going to have the same exact tie line. Okay, so if you want to determine the composition of the B-rich and A-rich layers at an original solution composition of 70% B and 30% A, okay, it's going to be the same exact composition as our first solution. Okay, so the composition of the A-rich layer is going to be the same, and the composition of the B-rich layer is going to be the same too. Okay, so this makes sense after all because we're at a constant temperature. Okay, so at a constant temperature, we have the same solubilities of A in B and B in A. So regardless of the original composition of our mixture, okay, so the components are just going to distribute themselves into these two layers according to the corresponding mutual solubilities. Okay, so it's only when we start to increase the temperature do we see changes in the corresponding composition of the A-rich and B-rich layers. Okay, so to give you guys a picture of what's happening here exactly, okay, so let's look at how a 40% B system is going to look like. Okay, so you have your corresponding A-rich layer and B-rich layer. Okay, so note that since we have a lot more A in this case, so you're going to have a lot of A-rich layer. Okay, so this is in contrast to another system over here that is just 30% A. Okay, so since you have less A, you have less of your A-rich layer. But note, however, that the composition of this A-rich layer is going to be the same. Okay, so we just have a different distribution of our entire mixture based on the corresponding amounts of the original A and B in the solution. Okay, but again, they're just going to distribute themselves into the corresponding A-rich and B-rich layers. But keep in mind, however, that the corresponding compositions of those A-rich and B-rich layers are going to be constant. Okay, so these distributions into the A-rich versus B-rich layer are just determined by the lever rule. Okay, so note here, so if you want to determine the amount of A-rich layer, okay, so for this particular composition over here, you have a very large distance d2, okay? So for this particular composition, however, you have a smaller distance d2, therefore you have a smaller amount of your solution that distributed itself into the A-rich layer. Okay, so we could try out the lever rule for our next problem here. Okay, so in our problem over here, we have a phenol and water system. Okay, so this forms a partially miscible binary liquid at low temperatures. So we're given an original mixture that contains 7 moles of phenol and 30 moles of water. Okay, so overall we have a 10 mole solution, okay, that is 70% phenol and 30% water. Okay, so based on this phase diagram then, so we have 70% phenol, right? So that is represented by this point over here. Okay, so 70% phenol, okay? So we want to know the composition of the phenol-rich layers and water-rich layers at 220 degrees Celsius, okay? So that is this temperature over here, okay? So if we want to determine the compositions of those phenol-rich and water-rich layers, we draw the tie lines and see where it intersects, okay? So over here, the intersection at this point over here, this tells us the composition of the phenol-rich layer. Okay, so now that we have a lot of phenol in this case, so therefore phenol acts as the solvent. Okay, so this tells us that the phenol-rich layer is going to be 90% phenol and just 10% water. Okay, so this is for the phenol-rich layer. Okay, so for the water-rich layer on the other hand, okay, so this looks pretty symmetrical. Okay, so for the water-rich layer, we have 10% phenol and 90% water. Okay, so this again is for the water-rich layer. Okay, so this answer is A. Okay, so how about for B? Okay, so B is asking for the number of moles of the original solution that is distributed into the water-rich versus phenol-rich layers at 220 degrees Celsius. Okay, so what we're doing here is that we're going to be using the lever rule. Okay, so again, this point here tells us the water-rich layer. This point here tells us the phenol-rich layer. Okay, so we need to make use of the lever rule, right? Okay, so this is distance 1. And this is distance 2. Okay, so in order to determine the mole fraction that got distributed into the water-rich layer, okay, we need to use the opposite distance. So that is d2, okay, over the total distance, d1 plus d2. Okay, so d2, that is equal to, so let's use the x-axis values, so the percent of phenol, so that is 90 minus 70, so this is equal to 20. Okay, so for d1 on the other hand, that is 70 minus 10, so that is 60. So the overall distance over here, this is going to be equal to 90 minus 10, so that is 80. Okay, so D2, that is equal to 20 over 80. So the mole fraction of the solution that got distributed into the water-rich layer, that is equal to 0.25. Okay, so since we're dealing with a 10 mole solution, okay, so 10 moles of this is just 2.5 moles. Okay, so for the phenol-rich layer, on the other hand, that is just going to be D1 over the total distance, D1 plus D2. So that is 60 over 80. So that is 0.75. So since we're dealing again with a 10 mole solution, we have 7.5 moles of our solution that got distributed into the phenol-rich layer. Okay, so overall that answers question B. Okay, so we can still use the same values over here to calculate C. Okay, so C is asking for the number of moles of phenol that got distributed into the water-rich versus phenol-rich layers. So we could use the compositions of our phenol-rich and our water-rich layers and the number of moles of solution that got distributed into those layers to calculate C. So let's just move on to a fresh slide over here. Okay, so if we're determining the number of moles of phenol that got distributed into the water-rich layer, okay, so our water-rich layer is 2.5 moles, and it is made up of 10% phenol, right? Okay, so 10% of 2.5 moles, that is 0.25 moles of phenol in the water-rich layer. Okay, so for the phenol-rich layer, okay, this is 7.5 moles, right, from item B. Okay, so in the phenol-rich layer, we have 90% of phenol based over here. So that was 90%, right? Okay, so 90% of 7.5 moles, that is 6.75 moles of phenol. Okay, so we have 6.75 moles of phenol in the phenol-rich layer and 0.25 moles of phenol in the water-rich layer. Okay, so just to check the law of conservation of mass, so if you add these two things together, you get a total of 7 moles of phenol for the entire system. Okay, so this is consistent with the given. Okay, so overall that answer is C. Okay, so now let's check out D. Okay, so D is just asking us for the temperature at which the water-rich layer will be 20% phenol. Okay, so if we start with a 70% solution over here, okay, and then if we increase the temperature to some temperature, okay, so we're looking for when the water-rich layer is going to be 20% phenol, okay? So 20% phenol is over here, okay? So let's bring that up to the curve over here. So we could see that if we have our original mixture here and we bring it up to 260 degrees Celsius, okay, the water-rich layer is going to be 20% phenol. Okay, so the answer to this is 260 degrees Celsius. Okay, so actually it doesn't really matter what the composition of the original mixture is going to be, just so long as it's within the curve over here. Okay, so at 260 degrees Celsius, the composition of the water-rich layer is always going to be 20% phenol. Okay. Okay, so hopefully this problem helped you understand partially miscible binary liquid systems. So keep in mind this is very similar to our liquid-liquid-liquid ternary system in which we had partial miscibility between two of our components. Okay, so now that we're familiar with the corresponding partial miscibility of the liquid state in our binary liquid system, okay, so if we're going to be considering the liquid-vapor equilibrium for these types of systems, okay, keep in mind that if we go beyond the critical temperature, we now have a completely miscible binary liquid system. Okay, so actually beyond this temperature now, the critical temperature, okay, we pretty much have a system again that is completely miscible. Okay, so that means the liquid vapor equilibrium can be very, very similar to our non-ideal completely miscible binary liquid system. Okay, so keep in mind that we expect that this is going to be non-ideal because we expect that the interactions between our components A and B are not going to be similar. Okay, so this is by virtue of the fact that we have partial miscibility at low temperatures. Okay, so there are going to be cases, however, in which the critical temperature is going to be above the boiling point of the mixture. Okay, so this is when we have more complex phase diagrams in which the binodal curve here starts to intersect with the azeotropic curve over here. Okay, but for the most part, we won't be discussing this diagram too much. So this is just to give you a preview of the liquid vapor equilibrium of partially miscible binary liquids. Okay, so now let's move on to our third and final case for binary liquid systems. Okay, so this is a case when we have a completely immiscible binary liquid system. Okay, so again, let's consider components A and B. Okay, so component A and component B. Okay, so of course each of these components are going to have their corresponding pure vapor pressures. Okay, so if we mix them together, okay, so since these components are going to be completely immiscible in one another, we're going to be forming two layers. Okay, so of course keep in mind again that the arrangement of these layers, okay, from top to bottom are going to depend on the densities. Okay, so the next question is, what is going to be the vapor pressure now of our solution in which we have complete immiscibility? Okay, so recall again Dalton's law. Okay, so we know that the pressure of the mixture is going to be equal to the partial pressure of component A plus the partial pressure of component B. Okay, so what's going to be different in this case, however, compared to the completely miscible binary liquid system is that when we had a completely miscible binary liquid system, we had to take into account the interactions of component A and component B with one another. Okay, this time, however, A and B do not interact with one another, okay, except of course for the very limited interface between the two layers. Okay, but for the most part they pretty much keep to themselves. Okay, so you just have a layer here of pure A and a layer here of pure B. Okay, so actually when we look at the overall vapor pressure then of our mixture, it's just going to be the sum of the vapor pressure of pure component A plus the vapor pressure of pure component B. Okay, so you do not have to take into account Raoult's law anymore because our components do not interact with one another. Okay, so you just have a system of pure A plus pure B in one container. Okay, so ultimately the partial pressures of the components in the mixture are the same as in the pure components. So overall, the partial pressure of our mixture is going to be independent of composition. So again, it's just going to be dependent on the corresponding pure vapor pressures of our components. Okay, so if we calculate the corresponding vapor pressure of our mixture, we could take into account the pressure temperature diagrams of our components. Okay, so note here that this is very similar to our pure component systems, right? So actually these curves over here, these can be approximated using the Clapeyron equation, right? Okay, so these are just our Clausius-Clapeyron curves for component A and component B. Okay, so let's just allow B to be the more volatile component. Okay, so since it's the more volatile component, its vapor pressure curve is going to be higher than that of A. Okay, so let's consider what happens at a constant temperature. Okay, so at constant temperature, we could figure out the vapor pressure of our mixture just by adding the vapor pressures of our components at the corresponding temperature. Okay, so this is the vapor pressure of component B, this is the vapor pressure of component A. So if we add these two things together, okay, we end up with a curve that corresponds to the vapor pressure of the mixture. Okay, so keep in mind again that it's just the addition of these two curves over here. Okay, so know that the curve is going to be higher. Okay, so this has implication in terms of the corresponding boiling temperatures of the mixture versus the pure components at constant pressure conditions. Okay, so let's consider the boiling temperature at an external pressure of 1 atmosphere. Okay, so if we look at the boiling temperature of component A, okay, it's going to be this over here. Okay, so pure boiling temperature of A at 1 atmosphere. Okay, so we also see the boiling temperature of component B. So if, however, we consider the boiling temperature of the mixture, it's always going to be lower than either of the components. Okay, so this is one of the principles to keep in mind for completely immiscible binary liquids. So the mixture will always boil at a lower temperature than the pure components. Okay, so this is due to the fact that the mixture is going to have a higher vapor pressure than either of the two components because it's an addition of those two vapor pressures. Okay, so the implications of this is very useful for steam distillation applications. Okay, so steam distillation, this is a distillation technique that allows for the separation of heat-sensitive materials. Okay, so these heat-sensitive materials, they have to be immiscible with water. Okay, so these are usually used for oils or non-polar organic compounds. So steam distillation allows the separation of these components at much lower temperatures. Okay, so since we're using steam, it's going to be less than 100 degrees Celsius. Okay, so it does so by introducing steam into the distillation process. Okay, so over here, you have your water, your steam generator. Okay, so you just heat your steam generator and then you allow your steam to enter your mixture to be steam distilled. Okay, so actually the application of heat to your mixture is optional. Okay, so if you allow steam to enter here, okay, so you introduce heat into the system, okay, and you allow your mixture to also boil, okay, at a much lower temperature than 100 degrees Celsius, okay. So the system that enters the condenser over here is going to be a mixture of both steam and your desired component. So your distillate then is going to be made up of a mixture of water and your desired component, okay. So even though your distillate is going to be contaminated with water, since your desired component is immiscible with water, okay, so you could easily separate those two immiscible layers. Okay, so we could do some calculations over here. Okay, so the calculations that we could perform can involve the composition of the vapor. Okay, so this will essentially be the composition of your distillate. Okay, so based on Dalton's law, we have this principle over here. Okay, so the overall vapor pressure of your mixture is just going to be the sum of the pure vapor pressures. Okay, so that means if we're going to be calculating the composition of the vapor, okay, so let's say that we want to get the mole fraction of water in the vapor. Okay, so this is just going to be equal to the vapor pressure of your water over the vapor pressure of the entire mixture. Okay, since the vapor pressure of water in the mixture is pretty much just the pure vapor pressure of water, okay, we could calculate the mole fraction of water in the vapor as just the pure vapor pressure of water over the sum of the pure vapor pressures of our components. Okay, so same thing goes for the mole fraction of X in the mixture. Okay, so this is just going to be, okay, so the vapor pressure of component X in the mixture. Okay, so this is equal to the pure vapor pressure. Okay, so this is just going to be equal to P naught X, okay, so the pure vapor pressure of component X over the sum of the pure vapor pressures. Okay, so we could use these equations, okay, to solve for our next problem here. Okay, so in this particular problem, we'll be steam distilling limonene from lemon rinds, okay, at 77 degrees Celsius and 1 atmosphere, okay. So if we want to extract 100 grams of limonene, okay, we want to determine how much steam in grams is required given that the vapor pressure of water at 77 degrees Celsius is 314.1 torr. Okay, so the application of this problem is that we get to know how much steam is going to steam distill along with the desired component, which is limonene. Okay, so this could tell us how much water is going to be contaminating our limonene in our distillate. Okay, so first and foremost, let's write down some equations that we know. Okay, so from this we could figure out the mole fraction of water in the distillate. Okay, so this is going to be given by the pure vapor pressure of water at the corresponding temperature over the total pressure of the mixture. Okay, so the trick here is to realize that when steam distillation occurs at 77 degrees Celsius and 1 atmosphere, okay, the vapor pressure of the mixture is going to be equal to 1 atmosphere. Okay, so that means we don't really need to know the corresponding vapor pressure of our desired component, which is limonene. Okay, so overall we could figure out the value for this over here. Okay, so this is going to be equal to 314.1 torr, okay, divided by 1 atmosphere. Okay, so let's convert the 1 atmosphere to 760. Okay, so that is going to be 760 torr. Okay, so overall this will allow us to calculate the mole fraction of water in the distillate. Okay, but we want to know the mass of the water in grams. Okay, so this is straightforward because we could get an expression for this over here. Okay, so we know that mole fraction is just moles of water over the total number of moles in the system, which is moles water plus moles of your limonene. Okay, so that means we could expand these expressions of moles in terms of grams. Okay, so overall number of moles of water that is given by, okay, so let's let X be mass of steam in grams. Okay, so overall we could express this as X over the molecular weight of water, so that is 18.02 grams per mole, divided by, okay, so number of moles of water, so that's X, okay, mass of steam in grams over 18.02 grams per mole, plus the mass of limonene, so we wish to extract 100 grams of limonene. Okay, so divide this by the corresponding molecular weight of limonene to get the moles of limonene. So 136.23 grams per mole. Okay, so overall we have this equation over here. This over here. Okay, so we could easily solve for x then. Okay, so upon solving for x, okay, this will give us the mass of steam in grams. So that is 9.32 grams. Okay, so if we steam distill limonene and we collect 100 grams of limonene, okay, in the distillate we'll also have 9.32 grams of water. So overall, we just discussed different binary liquid systems. Okay, so first we discussed completely miscible systems. Okay, and then we discussed the ideal case versus non-ideal cases. And we also discussed partially miscible binary liquid systems, followed by completely immiscible binary liquid systems and its applications in steam distillation. Okay,